Okay. Oh, this is very loud. Okay, so good morning, everybody, to our lecture today. So this is actually the last lecture before reading week. So after today, we have some break. And this will also be basically the last lecture where we talk about content that will be relevant for the midterm exam. So the midterm exam will take place in 2 weeks, right? On Friday, more than 2 weeks. Friday, March 24. Okay, so this is the date that I already communicated. So this should all be well known. And here on this slide, I just provide some additional information about the midterm, but nothing of that will be, I'm pretty sure, super unexpected. So it's pretty standard midterm. I'm simply going through that to make sure that everybody has kind of the same understanding. Okay? So daytime location, Friday, March 24, 7:30 to 8:30, meaning midterm is like 1 hour exam. Okay? It's purely in person. There is no online option. Okay, so very standard traditional midterm on campus. We will have 2 or 3 different lecture rooms, and we will assign every student to a specific lecture room via student ID or name, and we will publish that closer to the date. Okay? So the midterm structure will also be very simple and standard. There will be 3 types of questions. We will have multiple choice questions. We will have text-based questions, and we will have calculations. Okay? So I do not guarantee you the exact proportions, but you can expect that all 3 of them play an important role, not necessarily equally, but yeah, somewhat. All of them are important. Okay? Multiple choice questions, yeah, I think you know how that works. Text-based questions, there is one aspect of text-based questions that I would like to highlight a little bit. It's always kind of important how the question is framed and how the question is asked, okay? So especially you should pay attention to the wording. So if the question is like, name 3 elements of a car, I mean, it literally means name it. You don't have to explain. You just write steering wheel, engine, and wheels, or whatever. Okay? If it says explain why cars need an engine to drive, or whatever, you should briefly explain, like in 2 or 3 sentences, briefly explain, make clear why this is the case, but you don't have to write an essay, not 15 sentences, okay? If it's like discuss, this indicates that you should have a bit more of an in-depth discussion on this issue. So this would be, I don't know, discuss whether the government should subsidize electric cars or something like that. I mean, obviously you cannot just write 2 sentences. Okay? So the whole point here is I would like to make you aware that the terminology kind of matters, name versus explain versus discuss. Okay? The midterm will be 1 hour, as I said before. So you should obviously be careful about your time management. So don't run out of time. And if, for example, a question is name 3 elements and you write a 20-sentence essay, you will surely run out of time. Okay? What is the content for the lecture? Oh, for the midterm? Unit 1 to 3. So this is Unit 1 was the introduction. Unit 2 was portfolio theory 1, and Unit 3 is portfolio theory 2. So Unit 3 we will finish today. by finishing the chapter on the index model. Okay? So the corresponding sessions of the tutorial are 1 to 5. So this is the content for the midterm. Everything we do after that, so probably we will not start Unit 4 today, so probably we will do that after reading week. But everything after that will not be relevant for the midterm. Okay? Midterm, Unit 1 to 3, tutorial 1 to 5. Within the tutorial, within the lecture, everything is relevant that was ever discussed, said, shown, everything is relevant within the lecture and the tutorial. Okay? As I said in the very beginning, the textbook is the textbook is an additional reading in a sense. So aspects that were not discussed in the lecture, but that are only covered by the textbook, those aspects would not be relevant. Okay? So if you have any questions, then just let me know. But I think it's all pretty standard. Regulations, it's a closed book exam, so there is no additional cheat sheets or whatever. Of course, you can use a calculator. The list of calculators approved by the examination secretary can be found online, and you should check that your calculator is on that list. Okay? And last important point here, there will be a formula sheet. Okay, so you don't have to learn these formulas. And the formula sheet, we will provide it to you. So it will actually be attached to the questions paper. I will also upload this formula sheet on Moodle so that you can see which formulas will be provided to you during the exam. But this is for your information only, and you should not print that out and bring it to the exam. Okay, so it will be provided. Okay, so it's basically just the basic formulas. So nothing to be surprised about. And the last point, because we had some issues with that in the past, I really just want to make you aware to bring your own pens, pencils, erasers, and calculator. So the TA, the invigilators, we are not able to help. We have a couple hundred students who are doing the midterm at the same time, so we will not be able to help individual students who forgot their pencil or something like that. So just be aware, it's your responsibility to bring those things to the exam venue. Okay? Good. Is that clear? Any questions? No. Good. Yeah, I think there is really nothing special about the midterm. It's a very standard midterm. Okay? Good. So I will also upload these slides on Moodle this evening. Okay, so this is more or less where we stopped last week. The Markowitz portfolio selection model. So we talked a lot about portfolio selection, we talked about different worlds, we started with this one risk-free asset, one risky asset world, and then we made the world increasingly, or we changed the world step to step. First we said, look, now we take away the risk-free asset, we only look at the two risky asset world. Then we combined those two worlds in a one risk-free, two risky assets world. And then, finally, we moved to a multiple risky asset world. Okay, so that's the Markowitz portfolio selection theory. Or theories, that's, people sometimes call it theory, sometimes they call it model. Actually, theory is probably a bit too much, because there is no deep underlying theory behind it. It's kind of a nice idea, and it's a it's a nice thought, and it's actually the foundation of many of the modern asset pricing theories. But the Markowitz model itself is not very theoretical in a sense. Okay. So probably the most striking result of the Markowitz idea or the Markowitz model is really the separation property. So the separation property, if you remember, tells us that basically there are two individual tasks in optimal portfolio selection. The first task is to identify the optimal risky portfolio P, right? So we said basically identifying this optimal risky portfolio P, if you remember, I mean, that's purely technical. It's purely technical. Basically what you do is you have to find the efficient frontier in your universe. And once you found the efficient frontier, what you do is you find a tangency line to the sufficient frontier. And the tangency point, that will actually give you the optimal risky portfolio P. So this determination of this optimal risky portfolio is really purely technical. Okay? There is no influence whatsoever of the investor characteristics. It's the same for every investor. What depends on the individual investor is, of course, how much of your money you allocate to the risk-free asset and how much you allocate to this optimal risky portfolio P. That will depend on the risk aversion of the investor. Remember, that's the Y star. Y star equals what? What is the optimal fraction? Optimal fraction, Y star, was, if you remember, the risk premium of the risky portfolio, ERP minus RF, divided by the risk of the risky portfolio, sigma P squared, times the level of risk aversion of the investor. I mean, even without kind of learning this formula, it's kind of relatively clear, right? I mean, if the risk premium is higher, I invest more in the risky stuff. If the risk is higher, I invest less in the risky portfolio. And if I'm more risk averse, I also invest less in the risky portfolio. That's basically what this formula tells us. So 2 steps. First, find optimal risky portfolio. Second, find optimal complete portfolio. Both are completely separated. Both are 2 individual tasks. So this portfolio selection model, one of the big implications that this has is actually that if people follow this idea, if people identify the sufficient frontier and then they draw this tangency line and come up with the optimal risky portfolio, then actually in a perfect world, all people, all investors should hold the same optimal risky portfolio P. Right? Is that true? Not exactly. Right? I mean, of course, we all hold, if we invest in the stock market, we likely all hold slightly different portfolios. But what people have seen, or when you look at that, it's actually, those portfolios tend to be relatively similar or at least highly correlated. Tend to be, but there are differences. So the question really arises, does the fact that in reality people hold slightly different portfolios, does this mean that the Markowitz idea is not valid, or is there another explanation for that? And there are at least 2 reasons why people in reality do not hold exactly the same portfolios. One, different input sets. And the idea is very simple. We have a pencil here. Whoops. Different input sets. So basically, how do you find the optimal risky portfolio? I mean, we have our space here, expected return risk space. So here is the risk-free asset. So here are all our assets, right? And what we then do is we find the efficient frontier, this one here, and then this is P. Right? Very simple. It's more difficult to find a pencil that works. Okay, so this is the optimal risky portfolio P, right? That is clear, right? I mean, this is really the basic, what we talked about the last week. Okay? So, I forgot, this is expected return, this is risk. Okay? Right? So this is I'm an investment manager, I draw this thing, this is my optimal risky portfolio P. So what could now happen is that you are another investment manager and you try to do the same thing. But you think I'm not such a good investment manager because my input set, my estimations, my expectations about the risk of individual assets, that's right wrong. You think actually, let's say this here is Tesla. You actually think Tesla shouldn't be here, but Tesla should be here. You think I underestimate Tesla's expected return. If you do that, I mean, you draw Tesla here and not here. And what that means is that for you, the efficient frontier, because now also all the portfolio combinations are slightly different, right? Now your efficient frontier will be slightly different from my efficient frontier. Right? Now you do the same thing, you find the tangency line. So your optimal risky portfolio P will be slightly different from my optimal risky portfolio P. Because I use a different input set than what you use. And this could be I have a different expectation about the expected returns of some stocks, or I have different expectation about the covariance, the correlation of some stocks. And if that is true, then actually, yeah, our optimal risky portfolios will not be exactly the same. Okay? So the fact that in reality people do not hold exactly the same optimal risky portfolio could also be explained by the fact that people do not use exactly the same input lists. Okay? Because remember, I mean, in theory, when we do that, I mean, things are pretty simple. I tell you the expected return is 5%, and I tell you the covariance is whatever. Right? But in reality, we don't know the truth. We have to estimate these parameters from the data. And most of the time, we talked about that, people are lazy. They just use historical data to estimate that. But there are trade-offs, and there is no golden standard. It could be that I use 5 years of past observations and you use 10 years. We will end up with slightly different parameters. And that means slightly different efficient frontiers, and that means slightly different optimal risky portfolios. So my whole point here is that the fact that we see different optimal risky portfolios in practice does not necessarily mean that Markowitz is wrong. Okay? We will see, and this is something we will do after reading week. We will see actually that this whole discussion here is very crucial for the capital asset pricing model. The capital asset pricing model actually will have to assume, and this is the fundamental assumption of the capital asset pricing model. It will assume that everyone has the same optimal risky portfolio P. So basically what the assumption is that everyone has the same input set. The capital asset pricing model will call that homogeneous expectations. This is the fundamental assumption of the capital asset pricing model, the most criticized assumption of the capital asset pricing model, and actually the assumption that you cannot relax. Once you relax that, the whole model collapses. Okay? So one of the most famous models in finance, CAPM, is really based on this idea. The model says, in the theory, you need the same optimal risky portfolio P for everyone. In practice, we know that this is not the case. Probably because people use different input sets. And the second reason why in practice this optimal risky portfolio P might be somewhat different is that some investors could have investment constraints, right? I mean, the world is relatively, the financial world is somewhat integrated, but not perfectly. So if I'm a Hong Kong-based investor, I mean, it's relatively easy for me, very easy for me to buy Hong Kong stocks, right? It's still somewhat easy for me to buy Chinese stocks. But I mean, it's already a bit hard for me to buy South African stocks or stocks from some other country. And the same is true for US-based investors, for example. For them, it might be harder to buy small-cap Chinese stocks. Okay? So some investors, because of their geographical location, they can face some investment restrictions. And this can lead, for example, to a situation that some of these assets here, they are just not available for some investors. Okay? So if an asset is not available, I mean, again, you have to redo all the calculations of all the portfolios. Again, your efficient frontier will move and your optimal P will move. So that's another potential reason why P star, the optimal risky portfolio, is somewhat different in practice. Okay? Clear? Questions? Good. So this brings us to the index model, and the index model is actually quite related to my drawing here and the whole discussion we just had. The index model starts from the observation that actually the Markowitz model is very hard to estimate. It's very difficult to estimate. Why? Because we need a lot of parameters. Again, remember, what means estimating the Markowitz model? Basically, this means drawing the efficient frontier. Right? I mean, once you have the efficient frontier, things are simple. But calculating the efficient frontier requires that you know all the individual assets, all the black dots here. And if I would have a green pencil here, I would draw portfolios. The portfolios, let's just say portfolios are larger, these circles. So if I have 10 assets, 10 risky assets, I can form millions of different portfolios, right? And in order to calculate the efficient frontier, I have to form all these portfolios to know what the efficient frontier looks like. Now, the main problem is that for every risky asset, we need to estimate its expected return. Otherwise, we cannot draw it in this space, right? We need to know the expected return. We need to know its variance, right? And then in order to form these circles, these portfolios, we need to know the correlation of every asset with every other asset. So basically, we need to know the pairwise correlations. Okay? And this leads to a lot of parameters that we need to estimate. If we have 50 securities, I mean, expected returns, it's kind of okay-ish. I mean, it's 50 expected returns, so we can download the data and do the calculations. Yeah, okay. 50 variances. Okay. But then we do not need 50 correlations. We need 1,225 correlations. Because we need the pairwise correlations of every risky asset with every other risky asset. So it's basically n squared minus n divided by 2. Okay? So why is it n squared? Well, because it's a pairwise correlation, so there is a quadratic increase. Minus n here comes from the fact that the covariance of one asset with itself is actually the variance. So that's why it's minus n, but that doesn't really matter. And the divided by 2 comes from the fact that the correlation of Google with Microsoft is the same as the correlation of Microsoft with Google. So the correlation of I with J is the same as J with I. But we still have this quadratic term here that's quite annoying, which lets the number of parameters that need to be estimated, it lets it just explode. 50 securities. which is of course not a very close to practice or to reality, yeah? And already 1,225 estimate parameters. I mean, set in the values. What happens if you have 3,000 securities? Suddenly you need millions of covariances. Or if you go to somewhat realistic universe of, I don't know, 50,000 risky assets. I mean, 50,000 squared is a large number. So, and don't get me wrong. I mean, estimating these covariances is not computationally difficult. I mean, of course, I can download these time series and I can just program something. I mean, it's very simple. Even a simple Excel formula can do that for you. The problem is not so much that this is computationally intensive. We can, of course, do that. We can use historical data and, yeah, sure. The problem is more that, remember, historical data is just a shortcut. It's just a cheap version of actually filling out the table. Remember the table, every row is a future state of the world. We said actually we're interested in the future states of the world. But because we are lazy, we typically just use historical data and pretend that every past observation is one potential state of the world. This has a lot of assumptions, and actually this is not perfect. This is a kind of a shortcut. So every parameter that we estimate will have some uncertainty about its estimation. We know that we are making a mistake, right? I mean, if I use historical data and I estimate the variance, I know it's not perfectly right, because I cannot observe the true underlying distribution, the true data generating process. I just use some realizations. Because of that, every parameter estimate comes with some error and some uncertainty. And that means if you estimate millions of parameters, or tens of millions, or even hundreds of millions, if we talk about the realistic universe of a couple 10,000 stocks, and every parameter has some uncertainty. I mean, you can expect that the efficient frontier, I mean, sure, you can calculate it. I mean, computationally, that's not so difficult. I mean, you can use a computer and let it calculate the efficient frontier for you. But if every parameter has uncertainty and actually error, and then you create something that is based on hundreds of millions of non-precisely estimated parameters, actually the result will not be very precise too. Okay? So this is this old idea of like whenever you do forecasting, right, but whenever you do some models, some modeling, there is this kind of silly saying, but there's a lot of truth in that, garbage in, garbage out. And if you feed the model with wrong stuff, I mean, sure, the model just does what it does. I mean, it doesn't care. You feed it parameters and the model gets estimated. But if the parameters are wrong, I mean, also the output will be wrong. Okay? So it's really a problem that we need to estimate so many parameters because of the estimation error that this incurs. So this is the first problem. We need to estimate so many parameters. The second problem that is also kind of related to how the industry or I mean, this is often done by equity analysts, how this analyst industry is structured, is really that analysts often feel very uncomfortable estimating all these correlations. And the reason is the way how they are structured. Typically, if you are an analyst firm or if you do equity analysis professionally, I mean, typically every analyst focuses on one industry, right? Or even only one firm. So if you focus on one firm, I mean, you know your firm very well. Let's say I'm an energy, I specialize in energy firms, so I know my energy firms very well. And you are an equity analyst and you specialize in, I don't know, IT firms. You know your IT firms very well. But it's very hard for me to estimate the correlation of my firm with your IT firm because I have no idea about the IT industry. And you have no idea about the energy industry. So it's very hard for us to do that. Conceptually, we would have to know all firms in the universe to really estimate the correlation. So that's another reason why actually these estimations are very difficult in practice. So that's the idea actually, or that's where factor models come. Or that's how the basic, that's the starting point of factor models. The idea of the factor model is very simple. The factor model says, look, it's bogus, it's impossible to estimate hundreds of millions of covariances precisely, so just let's stop that. Let's say we cannot do that. And let's try to understand where the co-movement is actually coming from. And then the factor model says, well, look, probably the co-movement just comes from the fact that all firms in the stock market move with some common factors, some macro shocks. And if that would be the case, then actually we don't need to estimate all these covariances. We just need to know how the firms move with this macro shock. And that would be sufficient to basically have a good idea about the correlation of stocks. Okay? So the factor model wants to get rid of this full covariance matrix, replace it by a smaller set of risk parameters, and the idea is really firms don't co-move for randomness. I mean, there are reasons why firms co-move, right? I mean, if you look at that, so these are three firms, these are two firms and the S&P 500. So here, this is S&P 500, orange is Apple, and this lighter blue is NVIDIA. They co-move, right? There is some correlation. But it seems the correlation is not purely random, right? I mean, this is actually COVID. So like beginning of 2020, the world learns about a new virus and everybody gets scared, so stock prices go down. So all of them, both NVIDIA and Apple and the S&P 500, all of them go down. And then later, actually, they all recover again at somewhat different speeds, but the general movement patterns seem to be somewhat correlated. Okay? And the idea here is that there is a common shock, a common factor, a macro factor that actually affects all the stocks at the same time, and this macro factor then generates co-movement. I will talk more about that and the details in a second. Okay? And actually, here, this is a kind of a bit confusing picture, I realized. But the message here is very simple. Stocks are highly correlated. So this is intra-cluster correlation. So for different, so these guys here for different areas. So let's just look at the yellow line. This is US, Americas. They basically take American stocks, all of them, and calculate pairwise correlations, just brute force a lot of data, and then they average. So there are thousands and 10,000s or 100,000s of pairwise correlations of US stocks, and then they take the average. And this is what you get here. It's roughly 0.85. So pretty high correlation, at 85% roughly in the US. So if you believe the factor model, what the factor model now would argue is that this correlation comes from the fact that all of them move with the same factor. Okay? And this is like, even if you look between clusters, between those different regions, there is a relatively high co-movement, actually always above 50%. So even stocks from completely different regions of the world, they are highly co-moving actually. So don't look at the exact numbers. So these are just the messages. Okay? So if we can now basically decompose the variation of stock returns into two components, into a systematic component, basically the macro shock that affects all firms at the same time, and a firm-specific shock. This would allow us to estimate something that is something like this efficient frontier with a much smaller parameter set. It's much easier because we will see that in this world, we will not need hundreds of thousands or millions of correlation. We will only need to know how sensitive each stock is to the macro shock. So for every stock, we will only have one additional parameter, which is its sensitivity to this macro shock. And that's it. We will not need the pairwise correlations, which is really the key and the core idea of the factor model. But keep in mind, and this is important to not forget right from the start, the factor models here, these are not big theories. This is not a big theory. Basically, what factor models are, they are descriptions of returns. And there is no proof of most of that what comes. So most of that, I will just assume that I can do that, and then you will have to believe me, kind of. So factor models are, I would not classify them as theory models. They are real practical applications. They are kind of simplifications. Okay? Ways to make basically the estimation of the efficient frontier more doable in practice. Okay? Keep that in mind. So, what does the model do? I mean, the model is actually not complicated. The idea is not complicated. What we do is we describe the return of a stock. So RI, this is the return of stock I. By two components, this is how we start. We will later extend it. Expected return and some unexpected part. Okay? So the expected return is what I, on average, expect in the future. So always remember this table with the different rows. So this is the average. Across all the future states, 5%, 10%. Let's say this is, I don't know, this is Microsoft, then the expected return across all the different states will probably somewhere around 10%. Okay? But of course I know that in every realization of the true world, in every future state, I will not get exactly 10%. There is always some uncertainty and some unexpected part. Okay? So in this unexpected part, in this first description here, this could be really literally anything. This could be a COVID shock. This could be Microsoft develops some new product that is super great, like ChatGPT or whatever. This could be a new competitor for Microsoft that makes Microsoft completely lose market share. Something like that. That could be all of that here. It's just some unexpected part. Okay? It's important to already keep in mind what the unexpected part here is. I mean, this is basically random noise, if you want, with mean 0 and a standard deviation of sigma I. It's just randomness, white noise, kind of. So why is it, by definition, why does it have an expected value of 0, a mean of 0? Well, quite obviously, because if it would have a positive mean, we could transfer the positive mean into the expectation. Right? Across all the shocks, we always make 1%. I mean, then the 1% is not unexpected, it's actually expected. So this is really the unexpected part, mean 0, and a standard deviation of sigma I. Yeah, so we assume that returns are jointly normally distributed. We always, as I said in one of the earlier lectures, we will always do that. It makes our life just much easier. So, but this is not yet the core of the index model. This is just really the start. So now what the index model does, and this is now getting closer to the core or the idea of the index model, it says, look, this unexpected part here, EI, actually, where is this coming from? And then the index model, and this is the idea of the index model, says it's coming from two parts. It's coming from macro shocks, or a macro shock, that affects all the firms at the same time. And it's coming from firm-specific shocks that, by definition, affect only a firm. So what we do is we split the EI at the beginning into two parts, into M and EI, or we remove the M part from the EI. It's probably the better way to say that. and this M part is an unexpected macro surprise. Again, the unexpected macro surprise has a mean of 0 because everything that would be expected could come into the expectation. And it has a standard deviation of sigma m. So what this is basically saying that, look, if there is an unexpected macro surprise, and what do I mean by unexpected macro surprise? I mean, this could be anything that affects all firms at the same time. It could be higher than expected inflation or lower than expected interest rates. It could be COVID. It could be literally anything that affects all firms at the same time. So it says, look, if there is a positive macro shock, let's say lower interest rates for everybody, then actually this will move the stocks of all firms. M here, if you pay attention, has no firm subscript. M is the same for all firms. It has no subscript I. EI has a subscript I because that's the firm-specific shock. That's Microsoft inventing ChatGPT or whatever. That's COVID. But of course, M is not only COVID. It's also like general economic development and every macro shock. So this, what we are talking about here, is a single factor model. So in the single factor model, we assume that we can summarize all these macro shocks in one parameter, in M. But it's relatively straightforward, and we will do that later when we develop arbitrage pricing theory. It's very straightforward to extend this to a multi-factor model where we simply have different macro shocks. Same idea. Good. So our macro shocks and also the firm-specific shocks, always keep in mind, those are surprises, shocks. Okay? This is the unexpected. The expected is always in the expectation. This is the unexpected macro shock. This is the unexpected firm-specific shock. So for example, if all investors expect inflation to be 10%, and then inflation is 11%, the macro surprise would be 1%. Just the difference between the expectation and the realization. It's always the unexpected part. And by the same idea, if we expect Apple to develop a lot of new great iPhones, then this would not be unexpected firm shock, but this would be already in the expectation. It would be a shock if suddenly Apple announces they stop producing iPhones because I don't know exactly why Apple would stop producing iPhones, but I don't know. They could say it's getting too expensive, or they lost a patent that was very crucial, so they cannot produce any more iPhones, something like that. So that would be completely surprising and unexpected, so this would be a firm-specific shock. Okay? Good. Our EIs, our firm-specific shocks, and are uncorrelated to M, right? Because M is like affecting all firms at the same time. EI is only affecting firms. Good. So this equation here is, there is one more step, but the idea behind this equation is really kind of the idea behind the factor model. The macro shock affects all firms at the same time. This here, very obviously, also how we derived it is not a proof. I mean, I cannot prove that this equation holds. It's just an idea, in a sense. And this is the factor model. It's the idea that we can describe returns via such equations, and that we can split risk into these two parts, into macro shocks and firm-specific shocks. Or you can also say into systematic risk and non-systematic risk. Okay? And again, it's not a proof. So if that is the case, if firms' returns would follow this equation, and they don't, because that's still very simplified, but we will get back to that. The only reason that there is, if you look at that, the only reason why stocks co-move is M. Right? Firm-specific shocks are firm-specific. They are not correlated with each other, and they are not correlated with M. So firm-specific shocks here cannot generate co-movement. The expectation can also not generate co-movement because it's just an expectation. It's not a random variable. So the only thing that could generate co-movement are those two things. This here is firm-specific, so it also goes away. So the only thing that is left is M. M generates co-movement. COVID hits, all stocks go down. So if this is the case, I mean, what is the risk of a stock? I mean, we can pretty easily write the risk of a stock as two parts, and this is again going back to the idea that the macro shock and the firm-specific shocks are not correlated, so that's why we can simply write it as the sum. If you remember, this is similar to when we talked about this complete portfolio of the risk-free asset and the risky portfolio P. We said, now, in this case, actually writing the risk is very simple because we assume that both are uncorrelated. So if they are uncorrelated, the risk of stock I, or the variance of the stock returns of firm I, consists of two parts, the variance of the macro shock and the variance of the firm-specific shocks. Makes sense? Right? I mean, if the macro shock more volatile, the stock is more volatile. If the firm-specific news are more volatile, it's also more volatile. The more interesting part is now, if we look at the covariance between any two stocks, I and J, in this universe. I mean, what is the covariance of I and J? Our I and RJ is basically nothing else than M, the macro shock, plus the firm-specific shocks of I, to M plus the firm-specific shocks of J. I mean, this is basically this equation here. As I said, the expectation, we can ignore that because that doesn't generate co-movement. And here we can even ignore the firm-specific part, right, EI and EJ, because they're also uncorrelated. They can also not generate co-movement. I mean, two things that are uncorrelated by definition. This is again how we define it. We say the firm-specific shock is purely firm-specific, and it's uncorrelated to the macro shock. If this holds, then the covariance of any two stocks is just the variance of the macro shock. Greatly simplified word, of course. But if that would hold, I mean, this would be the case. If you think about that for a second, of course, it's not like super realistic. Even the assumption that EI and EJ are absolutely uncorrelated is probably not super realistic, right? Because it could, of course, be that, let's say, Microsoft invents ChatGPT. I mean, obviously, this also affects Samsung and Google and other firms. So in reality, things are not perfectly firm-specific. There might be some correlation even among those shocks that we typically consider firm-specific shocks. Or, I don't know, BMW has a factory and it burns down. I mean, there are also some ways how this affects Toyota and other firms. But the factor model, again, doesn't care about that. It just says, oh, look, I as the factor model, I try to be simple. I want to simplify the world. So in a simplified world, there is zero correlation. So if we could perfectly distinguish macro and firm-specific shocks, actually there would be no correlation. So that's the idea of the factor model. Yeah? Good. So far we made one very crucial assumption. If I go back here, we made one very important assumption. And this is that the macro shock, M, affects all firms in the same way. Right? I mean, this would probably basically mean if you have firms I and J, and the macro surprise about GDP growth is plus 1%, so 1% more growth than expected, both I and J would go up 1%. Which is probably not the case. Right? Probably some firms are more sensitive to those macro shocks and other firms are less sensitive. And this we will do after the break. So we will extend the model to allow for these different sensitivities. Okay? But let's have the break first, 10 minutes break. Okay, so yeah, as I said, let's now in the next part try to make this single factor model more realistic. Okay? And one part that is clearly not realistic so far is really that now we assume that the macro factor, the macro shock M, affects all firms at the same time, in the same way. And this is just like one tiny little example that shows that this is actually not true. So what this is that here's a return of firms from two industries, from US automobile parts and US beverage industry over time. And what you see in this, with these gray bars here, they indicate times or periods of recession. And I don't want to really go too much into that, but if you look at the financial crisis, 08, 09, what you see is that, I mean, obviously there was a macro shock, less economic growth, and both US beverage, blue, and US automobile parts, red, both of them declined. But it's quite obvious if you look at it, like automobile parts declined by a very high amount, like 70%, and beverages only by about 20%. So if you think about the macro shock as economic growth, I think it's quite obvious that some firms or some industries are more exposed to that and other firms are less exposed to that. I mean, consider like firms that provide daily goods like beverages or food. I mean, even if we are in a recession, right? I mean, people still buy food, beverages, they buy drugs, pharmaceuticals, things like that. But of course, people adjust their spending behavior because if there is a recession, on average, people have less money to spend. So what they often do is they stop purchasing or postpone the purchase of more expensive goods like cars. So cars are actually one of the most hit industries in times of recessions because people, if they have less money, what they can do is they can postpone typically buying a new car, drive their old car just for a longer time, or they, instead of buying a new car, they go to the used car market and buy a used car. So the point here is some firms are more exposed to these macro shocks and some firms are less exposed to the macro shock in practice. So we should probably incorporate that in our factor model. And we can actually do that. So this is the factor model, our new factor model that allows for a different sensitivity of firms to the macro shock. So what we have now, the only new part here is the beta I. So we have now a firm-specific factor, beta I, that measures how sensitive a firm I is to the macro shock M. So you see the macro shock is still no firm index, so that's the same for all firms. But every firm can now have a unique sensitivity to that macro shock. So that's the beta coefficient. It's actually the same beta coefficient for those of you who are already familiar with the capital asset pricing model. It's the same beta coefficient as in the capital asset pricing model, but there's a very different way of deriving it, right? I mean, here we just say, oh yeah, let's introduce a sensitivity, bam, and that's beta. In the capital asset pricing model, we will actually theoretically derive what beta is and explain why it's there. And then we will see it's the same thing as here. So the product, the end product is the same. But the way how we derive it here is very ad hoc. We just say, oh, macro shock sounds reasonable, but firms should have different exposure. So let's introduce beta. Very ad hoc. The capital asset pricing model does this very theoretically. Okay? So if we do that, I mean, things don't change dramatically, but a little bit. So what is now the risk of the stock I? Well, sigma I squared, and again consists of two parts. The second part hasn't changed. It's the risk of the macro shock, the risk of the firm-specific shocks, sigma squared EI, same as before. And now we still have sigma m squared, so the risk of the macro shocks, but now this is scaled by beta I squared. So now if you think about that, now risk consists of two parts, and I will get back to that a little bit later. Risk consists of, this is risk, this consists of two parts. The first part here is the macro risk part. So this is actually systematic risk. How much the firm is exposed to the systematic risk, beta I, and how high the systematic risk is. And there's firm-specific risk. Okay? So this is still not really what the core of the index model here is, or why we are actually doing this. So the reason why we are doing this is really more the last equation here. The index model, even in this adjusted and more realistic form, now allows us to express the covariance between any two stocks as the variance of the macro shock times the two sensitivities of the stocks to the macro shock. The reason is the same as before. I mean, the expectation part here, that goes away, so it's basically beta I m plus EI to the with the covariance of this part with the same part of stock J. So these two parts here, EI and EJ, are by definition uncorrelated. So it's the covariance of beta I m with beta J m. So that's the variance of m times the two sensitivities. Okay? Good. So now you can already see the big advantage of the factor model. Now we can express the covariance between any two stocks in the universe by this relatively simple expression. And the biggest advantage here is, in order to measure the covariance of any two stocks, we only need to know the variance of the macro shock, which is one parameter. Even if you have a universe of 100,000 stocks, the variance of the macro shock is always one parameter. And we need to know the sensitivity of every stock to the macro shock. But now this scales with n and not with n squared. Right? I mean, if we have 100,000 stocks, we need 100,000 sensitivities. But we don't need 100,000 squared minus n divided by 2 covariances. So suddenly the problem of estimating basically the efficient frontier, it doesn't explode anymore if we add more and more stocks, because we got rid of the square. And even in very practical terms, I mean, if you think about that, as I said before, it's often very hard for me because I'm I don't know, what was I, energy firm analyst or so, and you are I forgot, pharmaceutical firm or whatever, IT firm. It's very hard for me to measure or to estimate the covariance of my energy firm with your IT firm, right? But now I don't have to do that anymore. I only have to know for my firm, how sensitive it is to the macro shock, and you tell me how sensitive your firm is to the macro shock, and then I can calculate the covariance between those two stocks. Very simple. I can focus on my firms, you focus on your firms, or both of us estimate beta I estimate beta I, you estimate beta J, then we just use the same formula and we are done. So that's really how simple the model is. Okay? But given, I mean, this is very appealing. It makes life very simple and very easy. But we should never forget, it's a descriptive model. It's not a theory. It's a description of returns, and if this actually really accurately describes returns or not, well, we are not totally sure about that. We have never proved that it is the case. Okay? So, but let's assume that the factor model does a reasonable job, and let's assume we can really split risk into these two parts, systematic and non-systematic risk. There is still one problem. And go back one slide. The problem that we are still having is that I always talk, I mean, you probably think, oh, but he's talking about the macro shock, but what exactly is the macro shock? I mean, it seems very opaque. Sometimes I say COVID is the macro shock, and then I say growth is the macro shock, and inflation or whatever. So here, it's just an equation. It's just the macro shock, the macro surprise that generates the co-movement, the systematic risk, and the one-factor model is actually silent about what that actually is. It's just any factor that affects firms, all firms at the same time. I mean, of course, in practice, probably there's not only one factor that affects all firms at the same time. Probably there are many factors. Inflation, exchange rates, growth, whatever. Yeah, you can think about it. Oil prices, things like that. Okay, interest rates, of course. But that wouldn't be a problem. I mean, we could then simply extend the one-factor model basically to a multi-factor model where we have like 5 factors. So we have 5 different macro shocks and 5 different sensitivities. So even in a 5-factor model, we get rid of the n squared. It's just 5 different sensitivities and not n squared or something. Good. So, but what is the macro shock? And this is actually the core problem here that we don't know. We don't know, which is bad, because the model started with this promise that it makes our life easier, and now it says, yeah, look, but actually there is a macro shock, but I don't know what the macro shock is, which is not very satisfactory for us. So we have to think about ways to solve this. And actually, the obvious ways, the more obvious ways, probably they will not really work. If you, for example, say, oh, the macro shock could be GDP growth or unexpected GDP growth. I mean, that's economic thinking, which is good. But in practical terms, that's pretty difficult, because how do you calculate unexpected GDP growth? It's not super easy. It's only available in very discrete time frequencies, like every quarter or so. And it's not even totally clear how to calculate the unexpected part. So what was the expectation? What is the unexpected part? So if you want to do that, actually really imagine you sit down in front of your computer and you want to do it. It's again very tricky. I think about inflation. I mean, there are a couple different inflation rates. It's unclear what the expectation is and what the realization is, and inflation data is only available quarterly, probably monthly, but it's not very high frequency. It's not very easy to work with. So that's why people had a good idea. And they said, look, this is all bad. We don't want to mess with this unexpected GDP growth and stuff, because we cannot really measure that. And keep in mind, this whole exercise is about practice, right? We want to estimate the efficient frontier, basically. So then people said, yeah, well, probably let's just use a broad stock index. And probably let's just use the return of a broad index. I mean, you can use S&P 500, you could use a MSCI World Index. I mean, in Hong Kong, you can use the tracker fund. I mean, just a broad index. And use this as the macro factor. Again, of course, this is not perfect, probably, likely. But it is appealing for the reason that it is very easy to observe past prices and returns for such an index. So for an S&P 500, we can observe hourly or even minute prices for the last 5 years, 10 years. So we can very easily estimate all these parameters that we need to estimate. Especially, it's very easy, and I will show you that in a few slides, to estimate the sensitivity, the beta, for every stock, if we use this index as the macro factor. Is this economically meaningful? Well, no, not too much, really, right? I mean, economically, we would like to use something like GDP growth or like really core risk factors that generate systematic risk, that generate co-movement. That would be economic thinking. But in practical terms, that's pretty difficult. So that's why people said, oh, let's take a shortcut and let's just use the S&P 500. So in some sense, the S&P 500 accumulates all the macro risks in one index, because this is like, if GDP growth is unexpected plus 1%, I mean, on average, we expect the S&P 500 to go up plus 1%. To go up, at least. So the S&P 500 index, in that sense, is a way to measure all these macro risks in one go, one index. Okay? Again, economically questionable. That makes sense. But it's very nice in terms of practice. So now we use the market index M to proxy for the corporate factor, and this is then called the index model. So the one factor model, here we had a single factor model, where the macro risk or the macro shock is actually the index. This is then called the single index model. Okay? Clear? Yes? Clear? Good. So let's now think about estimating the model. And the really nice thing about the single index model is that it will be very simple to estimate it. Okay, it's really very simple. What we do often, and this is how it is explained on the slides, but don't get too confused about it, we express it in excess returns. So capital R here would be the excess return, and the small r would be the actual return. The excess return is nothing else than the actual return minus the risk-free rate. So conceptually, if you estimate the single index model, that's actually the cleanest way to do it. In practice, people often don't do it. They just estimate it in plain terms. The difference is not dramatic, especially if RF is constant over your estimation period. Actually, there is no difference. If RF changes over your estimation period, there can be some difference, but it's often not too bad. At the end of this chapter, I will give you some practical recommendations, and one of them will be probably we don't need to estimate it in excess form. We can just estimate it in the normal form. But typically in textbooks, it's in excess form. It doesn't matter too much, it's the same thing. Don't get confused, that's what I want to say. So what does this tell us? This tells us the excess return of stock I at time t is alpha I plus beta I times the excess return of the market plus the firm-specific surprises at time t. So more slowly, what does that mean? Well, that means the excess return is alpha I if the market return is 0. So if the market return is 0, basically the excess return on the stock is alpha I on average. Because that is again just noise. Another way to say that is that this is actually alpha I is the excess return when there is no macro shock and there is no macro news. Or even one step further, I could say alpha I is the excess return, the expected excess return that I get if there is no systematic risk. So imagine there is a stock that has a beta I of 0. So this stock would not be affected by M, by the macro shock. right? It has no sensitivity, right? That's beta I 0. So what is the expected excess return of beta I? Well, the expected excess return of that stock with beta I equals 0 is exactly alpha I. Right? Clear? Beta I is 0. I mean, this term goes away. This term has mean 0. So if I take expectations here, it's alpha I. So this is actually the famous alpha. So people, this like stock invest forums like Seeking Alpha and stuff like that. So people seek alpha. They try to find alpha in stocks. And here, this is the first time we come across alpha. We will talk more about it in the future after the reading week. But alpha is really a non-systematic risk premium. Okay? So it's a risk premium that you get, even though there is no systematic risk. Okay? We will later see that all the equilibrium models tell us that only systematic risk should lead to a risk premium. Meaning that if you hold systematic risk in your portfolio, you will get higher expected return. And that is your risk premium for holding the risk. But it will only be about systematic risk. If you hold firm-specific risk, there will be no risk premium in the equilibrium models. This is a bit jumping ahead. Here, there is zero assumption about anything. This is not an equilibrium model. This is really just a description. So we can pretty much write whatever we want here. I'm just trying to tell you that alpha I, here, of course, I can write alpha I. I mean, it's just like math. Yeah? But the equilibrium models will actually tell us that alpha I goes away, is 0, is basically competed away. There is no risk premium in the absence of systematic risk. So here, we cannot see that yet. So it's kind of a little bit of a preview of what will come. Here again, we have no assumptions about equilibrium. We have just like a purely descriptive form, a way of describing returns. So then the return again consists of this non-risk premium part, the expected excess return when the risk is, systematic risk is basically 0, a risk premium, a systematic risk premium part, and a firm shocks. Okay? So I can take this one step further, and I can take expectations from both sides, which leads to something that looks close to the capital asset CAPM. Probably we should wait with that. But this is a bit, I mean, we can do that, but again, we have to keep in mind this is not a model. This is just like we are describing returns in a way we think it's meaningful, and then we do some restatement and some expectations, and this is what we get. If we do that, I mean, the result is interesting. It basically says as the expected return of any stock, I, equals alpha I, this here, alpha I, plus this part, beta I, the sensitivity of the stock to the index, times the excess return, the expected excess return on the index, plus nothing, because the expectation of this here is 0. Right? So this basically goes away. So, again, a bit jumping ahead, this will also be very similar to what we will see in the capital asset pricing model. If you assume that alpha I is 0, then the expected return of any stock will be a function of its systematic risk, of its co-movement with the index, which will actually be the core result of the capital asset pricing model. So the expected return is proportional to the systematic risk of stock I measured by its beta. How much the stock moves with the market. If a stock moves a lot, go back here, our US auto parts firms, they would have a high beta because they move a lot with the index. Our beverage firms would have a low beta because they are relatively stable over time. This now tells us that the expected returns on the automobile firms should now be higher than the expected return on the beverage firms, right? Because beverage firms have a low beta, so the expected return here will be low. Automobile firms have a high beta, so the expected returns will be high. Okay? And this is really the intuition is really that if you have a high systematic risk, yeah, people are only willing to hold that, to invest in that if they get compensated in terms of higher expected returns. Because remember, systematic risk, this is when we said that when we started to talk about it, systematic risk is really the part of the risk that you cannot diversify away. No matter how much you invest, and I will show you that in a second, no matter how many stocks you add, the systematic risk, this common shock part, that will always persist. Okay? So alpha I is then like the additional return that you get. So this part here is compensation for systematic risk. And alpha I is the part, the expected return, the excess return that you get in addition to this compensation for systematic risk. This is why people try to seek alpha, find alpha. Seeking alpha, investment managers want to find stocks with high alpha, because if you find a high alpha stock, you can get high expected return basically without taking risk. Okay? In market equilibrium, we will see in the equilibrium models, alpha will be 0. So this will be after reading week. We will talk about that. And then we will also talk about the empirical evidence that we have, which is a little bit mixed, but most evidence we have supports the idea that market efficiency is generally high, which would imply that alpha I should be low or even non-existent. Okay? But I will show you all of that. Clear? Good. Yeah, then this is actually basically the same thing that we did before with the single factor model. So we can now write the risk of stock I as two parts. This is the macro risk. So this is now a sigma squared of the index, and beta I is the sensitivity of stock I to the index returns squared, plus this firm-specific risk. Okay? And the covariance, same thing as before. If we have the covariance between any two stocks, is beta I, beta j, and the variance of M, and M is now the index. Okay? So now our life is actually quite simple, because we only need to estimate a limited number of parameters, and we use the index as the market macro shock, which is nice for us because we can easily download. We can go on Yahoo Finance or Google Finance or whatever, download S&P index returns, and we are nearly done. I mean, it's super simple. So where has this brought us? Well, this brought us to a situation that if we have like 50 security portfolio, or a universe here of 50 portfolios, in order to estimate the efficient frontier, to calculate all the portfolio combinations, we only now need 152 parameters instead of 1,325. What do we need? Well, one estimate for the market risk premium here. One estimate for the variance of the market, the index, but both are super simple. I mean, we can use historical data for the S&P 500, fill out our table, do the lazy approach, just assume that the past is a good predictor for the future, just average across the past 5 years or so, and this gives us the expected return. And same for the variance. Just use historical data. We need 50 estimates of alpha, 50 estimates of beta, and 50 estimates of the firm-specific variance here. We'll see, I will show you in a second how to do it. Basically, you can relatively safely ignore alpha because it will always be close to 0. So basically what you need is you need the betas and the firm-specific variances. Okay? So 152 parameters instead of 1,325. You could still say, look, I mean, yeah, it's good. We saved, what, 1,100 something parameters, but I don't care so much. Yeah, fine. I mean, you're right. I mean, it's probably for a 50 security portfolio, I mean, the difference is not too dramatic. But then my point would be, well, okay, let's look at more realistic scenario. Let's look at New York Stock Exchange, which has probably around 3,000 securities. If you estimate the index model, you need 9,000 parameters. If you estimate the full Merkowitz model, you need 4.5 million. And 3,000 is still not realistic for the universe, right? I mean, if you have a worldwide portfolio, I mean, you could easily end up with 20,000, 50,000 stocks. I mean, this is growing quickly. And it's basically impossible to estimate. Yeah, of course, I mean, as I said before, you can estimate. But if you have a tiny error and you have 4.5 million parameters and every parameter has a tiny estimation error, I mean, things add up. And this garbage in, garbage out idea is pretty much what we should have in mind here. Good. Let's just do a bit of, I mean, this is really not super, I mean, I'm sure you know all that this is very intuitive. Don't get confused by that. So let's now think about the index model and how diversification works in the index model. So I'm not proving that here, but things in the index model are always kind of simple. So if you have a portfolio, this is now the risk of a portfolio. If you have a portfolio, we can also decompose the risk of the portfolio returns into two parts. It's this orange box and the green box. And the orange box here is the systematic risk part, and the green box is the firm-specific risk part. So basically, the portfolio consists of two risks: systematic risk, or the average systematic risk of our stocks, because the sigma, the beta p, so the sensitivity of the stocks in the portfolio, this is nothing else than the average beta of all the stocks in the portfolio. So if you have an equally weighted portfolio of two stocks, one stock has a beta of 1, the other stock has a beta of 3, you get an average beta of 2. But you can easily calculate that. It's just the weight, the average. If it's equally weighted, if it's not equally weighted, you just add the weight. And the green part is the firm-specific part, and we will get back to that in a second. So the orange part here, you can see, if you add more and more stocks, the orange part will actually not disappear. Right? I mean, sigma m squared is independent of the size of your portfolio, and the beta of your portfolio is just the average of the betas that you add. So if you add more and more stock, I mean, this average can change, but it will not approach 0. So actually, in reality, if you add more and more stocks, beta will approach what? Which value? 1, right? Because if you add more and more stocks, and let's say you could use an index that really covers the whole market, in the extreme case, your portfolio would be equal to the market, and the beta of the market obviously is 1. Right? I mean, that's the sense how much you move with the market, and if you are the market, you move 1-to-1 with yourself. So if you add more and more stocks, beta will converge to 1, but it will not go away. Right? Sigma m squared will still be there. I mean, even if beta p is 1, sigma m squared will be a risk. So how about the sigma squared EPs? I mean, they are all independent and have 0 expected value. That is what we have to keep in mind. This is how we define firm-specific risk, right? I mean, it's always independent. It has 0 correlation with itself. It has 0 correlation with all other firms, and it has a mean of 0. So mathematically, you can easily show this, basically the law of large numbers. I mean, if you add more and more of that, basically everything overlays and the noise cancels out. If you add more and more noise, if you add an unlimited number of noisy things to your portfolio, the average variation will be 0 because all things cancel out. So if n goes up, actually what happens is that this part goes down. So we can show that actually this firm-specific part of the risk, the green box, assuming that all firms have the same firm-specific risk, approaches the average firm-specific risk, but 1 divided by n. So if n becomes very high, I mean, this approaches 0. Okay? So it's not approaching the average firm-specific risk, it's not approaching the average of a specific firm, it's approaching 0. And the intuition is really add more and more noise, then the noise starts canceling out, if the noise is completely uncorrelated. Okay? So this is actually diversification. So diversification means like the green part goes away, and if you graphically show that, I mean, we can simply easily see that this is n, so this is the number of stocks, and this is the portfolio risk. So we add more and more stocks. I mean, the systematic risk doesn't change. It stays there. Sigma m squared is fixed. But the firm-specific part goes away. Because adding more and more noise, the noise overlays, it cancels out. So, and if n goes to infinity, I mean, then the whole risk of the portfolio will be systematic risk. And I showed you last lecture or 2 lectures ago, actually you don't need to go to infinity. We know that even if you have 20, 30, 40, 50 stocks, you already get rid of a lot of the firm-specific risk. So of course, your diversification still improves if you go to 100 or 200, but the improve is it's declining. It's the improvement becomes smaller and smaller the more stocks you add. Okay. So let's now estimate the index model. So this is exactly what I showed you before. This is the excess return, this is alpha I, this is the excess return on the index, and here we use the S&P 500. This is beta I, so the sensitivity of stock I to the index returns. And this is the firm-specific shocks, the firm-specific surprises. Okay? So if we now do that for one example, let's say for Ford, we can estimate it. We can use data to estimate it, and it's actually very simple. So the excess return of Ford at time t is then alpha Ford plus beta Ford times the excess returns on the S&P 500 plus those residuals, these firm-specific shocks. Okay? I mean, estimating this equation is really not difficult. I mean, you could use monthly data, you could use weekly data. I show you later how to exactly do it. But even like in Excel, you can use the data analysis add-on and use the regression function to estimate this thing here. But there are literally hundreds of, no, probably not hundreds, but a lot of programs that you can use. You can use R, you can use data, you can use eFuse, you can use MATLAB, Excel, whatever you want. I mean, every program that is loosely related to math and statistics has some regression function. So let me show you a bit of the intuition. This is our data, and here we have the observation month. So this is month 0, this is month 60. This is the excess returns. And we have 2 time series. We have the market index and we have our Ford. So if we plot it like this, we can already see a little bit what's going on, but not yet very precisely. So there is already probably some indication that Ford moves more than the market. So here the market goes down, Ford goes down, the market goes down a bit, Ford goes down a lot, the market goes up a bit, Ford goes up a lot. But it's, I mean, it's just like eyeballing. It's not precise. So if you want to do this more precise, we actually have to do it like this. And this is the graphical, the graphical illustration of what the regression is actually doing. So what we do is we plot on the one axis the excess returns of the market index, and on the other axis we plot the excess returns of Ford. Okay? And now every dot, every point here represents one observation, meaning 1 month. So at this dot here, this is January 2012, the excess return on the market was 5.4%, and the excess return on Ford was 15.9%. So every dot here is a specific month observation, a specific monthly observation. Okay? So, and what is then the black line? Well, the black line is the regression line. So this is what the program, Excel or whatever R, does for us. So the program now tries to fit in a line in this space. And what is the condition? How does regression work? What is the condition for the line? Right, it wants to be as close as possible to all the points, right? And typically what you do is OLS, ordinary least squares, so that means what you do is you minimize the sum of the squared distances. So yeah, every point has a distance to the line, very simple. Then you square the distance, and you do this for every point, you build the sum, and then the line that minimizes this sum is the output of your regression. Okay? So that's, to some degree you can say that's the best possible way how to describe this linear relationship, this relationship in a linear way. Okay? So what does this line now tell us? I mean, basically two things. It shows us alpha and it shows us beta. Where can we see alpha?
On the point above the line, or above the line?
Nope. Yeah, this one. Right? This is alpha. So alpha, keep in mind, is the return that you expect to get, and the black line shows you the expectation, kind of the average. Unless there is some noise, the black line is what you get. If there is no systematic risk, so there is no excess return on the market, you get a return on Ford of, on average, what, -1%. Right? This is alpha, the intercept here. What is beta? Well, beta is the slope of this line, right? The slope of the line shows you how much Ford moves with the market. If the line is completely flat, the slope is 0, there is no co-movement. The slope goes up, there is more and more co-movement. Okay? So beta, these are the parameters that you get from the regression. Beta is actually the coefficient on the market index, the slope of this line. So our program here estimates this to be 1.32. And alpha is the intercept, which the program estimates to be about -1%. So this here and this slope. Okay? Of course, this all is not without uncertainty. So actually, both the intercept and the market index are estimated by the model with some uncertainty. And the model even tells us how uncertain it is about things. It tells us the standard error, the t-stat, and the p-value. So the p-value basically shows the probability that this coefficient estimate is simply 0, in simple terms. Okay? So if the p-value is high, we have not a lot of confidence that this coefficient is actually different from 0. So now if we look at alpha, alpha is roughly -1%, but the standard error is pretty high. It's nearly as high as the coefficient itself, which means the t-stat is very high, very low in a sense. The t-stat is nothing else than the coefficient divided by the standard error. And there is quite a bit of uncertainty. So actually the model tells us, well, look, there is some alpha here, but I'm really not sure if that alpha is negative or zero. So we really shouldn't, if we look at the output of these regression models, you should be really careful and keep in mind that there is always uncertainty behind it. I mean, the model tells you things with a precision of 4 decimal places. But this is misleading. The model is not sure this is the exact right coefficient. This is mathematically simply the coefficient, the slope of the line that minimizes the square distances. But there is a lot of uncertainty actually about these parameter estimates. And especially for alpha, the model already tells us that, look, yeah, alpha is negative here, but I'm really not sure if that alpha is really negative or in fact just zero. If that would be a real alpha, I mean, this would be pretty high. Right? This is minus 1%. We estimate this thing on monthly data. So annualized, this would be about 12%, even more than 12%. So a 12% alpha is pretty significant. That would mean you can earn 12% for that stock without taking market risk, systematic risk. And of course, it's a negative alpha, but that wouldn't matter too much because you can short the stock, so you get the negative alpha. Right? So if you're positive alpha, you long the stock. If you have negative alpha, you just short the stock. So seeking alpha is not about, you're not limiting yourself to plus or minus alphas. You're just trying to find alphas that are different from zero. But again, my point here, there's a lot of uncertainty. This alpha probably is just zero. Likely this is just zero. Even if it wouldn't be zero, it's unclear whether this tells us anything about the future or whether this is just a past thing. So we should be very careful and not use these regressions to find alpha. So these regressions are useful to find beta, but not really to find alpha. Okay? And the second thing I want to mention before, and then we have the break, also if you do your term project. I mean, I know when you do these calculations in Excel or also statistical programs, I mean, you can calculate the variance of a time series with a precision of 15 decimal places, right? But we should be aware that this is a kind of a nonsense approach. I mean, we know that there is uncertainty. We use historical data to estimate the future. Also, our approach is imperfect. So we shouldn't create this illusion of precision by stating 15 decimal places. So also for your term project, be aware. I mean, the things we do here, especially in the investment universe and when you do valuation and equity analysis, there's a lot of imprecision. It's not very precise. And we shouldn't create to others the illusion that we have a very high level of precision. Okay? So I'm not saying you shouldn't do that. Of course you should. I mean, you should use historical time series to estimate stuff. But when you describe things, probably don't quote 10 decimal places. And always be careful when you describe things and say, look, the variance is around something like, and not exactly 15.7892734%. Okay? Good. Let's have the second break now, and then we talk more about this regression outcome. Okay, so yeah, we just basically run this regression, that means we fit this line, and this is the output of the model. Okay, so the most important parameters we already discussed, the intercept is alpha, or the coefficient estimate for the intercept is alpha, and the coefficient estimate on the market index, that is actually beta. Okay? So there are a couple other things you can see from this output. You can take a look. It's not, so this is not the core that I want to discuss here. So the R squared, for example, here, the adjusted R squared here shows you that 38% of the variation in the forward returns, they can be explained by variation in the S&P returns. 38%. Intercept, minus 1%. But as I already said, statistical significance is not very strong. Actually, it's not statistically significant. It's not statistically different from zero. And even if it would be significant, if it would be different, we wouldn't be too confident that this is a good trading strategy, because all we did here was use historical data and run a regression. So even if we find positive alpha or negative alpha in past data, it's not a guarantee, and probably not even likely, that this tells us anything about the future. Okay? Good. Coefficient for the S&P 500, beta, is 1.32. There is a very high statistical significance, t-value of 6. So rule of thumb is everything above t-value of 2 would be considered significant, and below 2 is not significant. So p-value of 0, which means the model is very certain that this coefficient here is actually different from 0. Okay? The only issue we could have here is that the model, the regression tests whether the coefficient 1.3258, whether this is different from 0 or not. So this is what the t-stat and the p-value here tell us. But we know that beta shouldn't be 0, right? I mean, a beta of 0 would be very rare. I mean, that would be an asset that absolutely is unaffected by the market index. I mean, the risk-free asset, yes, but what else? I mean, it's not very common to have such an asset. So a probably more meaningful test here would be if the market index beta, if the beta here, 1.3258, if that is actually different from 1. Because we said 1 is kind of our baseline. If we have the market index itself is a beta of 1. So probably it makes more sense to test whether the forward beta is different from 1 and not whether it's different from 0. Because we know economically it should be different from 0. So how do we do that? Well, there is kind of one way how we can do it. We can take the coefficient 1.32, subtract 1, so that we kind of basically move it to the 0 test, because we want to test if it's different from 1. And then we divide that by the standard error, and we check if that is above 2 or not. So this is kind of a rule of thumb. So if we do that here, we get the coefficient 1.32 minus 1 divided by the standard error of 0.121. So the t-value here, this adjusted t-value, is roughly 1.5, which is below 1, below 2. So one thing we could conclude from here is that, yeah, the model estimates beta to be slightly higher than 1, but when we look at the uncertainty and the statistical significance of that, it's actually not really strong evidence that it's different from 1. It could also be just 1, which really shows how much noise you typically have if you estimate those things. Let me go back a bit. And this also kind of nicely connects to what we talked about before. I mean, remember I said there is always this question which time series you should use. The past 5 years, the past 10 years, the past 200 years. We said there is a trade-off. Longer time series, less noise. And Dow can clearly see that. I mean, if you add more and more data points here, very likely the estimation will become more precise, the model will become more confident, and the standard errors will go down. So the model will be more sure what the true alpha and what the true beta is if you add more data. But of course, keep in mind the other force is really that if you add more data from the past, you assume that the true underlying distribution or the data generating process, that they haven't changed over time, which is probably a reasonable assumption for the past couple of years, but probably not so much if you compare Apple today to Apple in 1985. Okay? So this is what we can see, and this is more or less the outcome. So this is the efficient frontier calculated with the full covariance model. So this is the Markowitz model that we had before, and the index model. Okay? And you can think about this picture as like a simulation exercise where you simulate data, so you actually truly know the covariance of everything because you generate it. So it's not actual real life data. It's just a simulation where you generate asset returns that have a specific covariance, and then you estimate on that universe where you know the covariance metrics, you estimate the full Markowitz model, and you estimate the index model. Okay? And what we see, and this is probably not surprising, is that the index model is not one-to-one equivalent to the Markowitz model. I mean, that would have been very surprising if we find that those two lines perfectly overlap, right? Because the index model obviously is a strong simplification of reality. It assumes all co-movement in the universe comes from the co-movement of stocks with the macro shock, the index. In reality, that might not be the case. I mean, firms' returns might be correlated for other reasons. I mean, I lose business, you gain business, something like that. Okay? So it's not exactly the same. But especially on this arm where you typically find the optimal risky portfolio, like in this area here, it's also not dramatically different. So it's kind of similar. And this is what you get for different parameters, for different simulations. It's not exactly the same. And especially here we have the minimum variance portfolio, right? The least risky portfolio that consists of risky assets. The minimum variance portfolios are very different. Here there's a lot of difference. But typically where the optimal risky portfolio P is in this area, there's quite a bit of overlap. So people showed that if you simulate that and if you do that, actually the optimal risky portfolio P is not the same, but it's somewhat similar in the index model and in the Markowitz model. Okay? So, long story short is, theoretically speaking, of course, the Markowitz model is better. If I can estimate the Markowitz model and if I know the true covariances and everything, I mean, yeah, I will always choose Markowitz. But if I don't know the true covariances, instead of estimating 3 million covariances, it's probably a better idea to use the index model, because your efficient frontier will be garbage, very likely, because you estimate so many parameters, errors on errors, so it's nearly impossible to estimate the efficient frontier. Okay? So the index model is a shortcut. It's economically not as well founded as the Markowitz model, obviously, but with real life data, if you estimate it, probably or very likely what you get as optimal risky portfolio P is more meaningful than what you get if you estimate the full Markowitz model. Okay? So it is a very practical model. It is very helpful. So how do you do that in practice? Or how do we estimate beta in practice? Well, people often use like 5 years of monthly data. Sometimes people use weekly data. Both is possible. It's common to use the S&P 500 as a proxy or as the index, but this is also not a must. So you can use a different index. What is often ignored are dividends. So you know, if dividends are paid out, that also you can adjust the returns for payouts. But given that this is a relatively people often ignore that because it makes life a bit more complex. And the index model in practice is also often estimated in plain return terms and not in excess return terms. So no capital R here. If we ignore basically the risk-free rate, this is okay if the risk-free rate is relatively constant over the sample period. If the risk-free rate is exactly the same over your whole sample period, actually there is no difference in the estimation. If it moves a little bit, it's still an okayish approximation. If the risk-free rate changes dramatically, probably you shouldn't do it. Okay? Good. So let me show you a clip that shows how actually the beta can be estimated with real-life data. And it's a little bit of jumping ahead. The guy in this video is doing one thing that we have not yet learned. When he does that, I will stop the video and I will tell you.
Hello and welcome. In this screencast, we'll take a look at how to compute the beta for a given stock. The beta is a measure of the volatility of and download some data from in this. Hello and welcome. In this screencast, we'll take a look at how to compute the beta for a given stock. The beta is a measure of the volatility of the stock relative to the stock market as a whole. So let's get started and download some data from Yahoo Finance. I'm going to download Amazon stock information. So if you go to historical prices and select weekly from, let's say, 2002, March 16th 2002, or let's say July 14th 2002 to July 14th 2012, get prices and go all the way down, download the spreadsheet. Now we can delete all information other than the adjusted close, and next we can download information from the S&P 500. Again, historical prices, July 14th 2002, and weekly, get prices, download the spreadsheet. Okay, now I'm just going to upload this into my working spreadsheet. So here's my data. I've copied the information from the two downloaded spreadsheets into my working spreadsheet. These are the Amazon closing prices. Now we need to calculate the returns.
Sorry. So just real quick. So first you see how simple this is. I mean, this literally takes 2 minutes or so. Because why is it so simple? Yeah, well, because we use the S&P as the index. If you would have to do research on macro shocks and how macro shocks affect stuff, I mean, that would take a long time. So this here you really see it's a shortcut, right? It's very simple. That's the first comment. A second comment, it's typically reasonable to use adjusted close prices. So there's open, high, low. I mean, you typically ignore that. You just use adjusted close. And the last comment here is it's very important if you do something like that. If you calculate beta, if you calculate variance of stock returns or whatever, don't do that on the prices. Do it on the returns. So sometimes in term projects I see groups, I mean it's rare, but sometimes calculating betas on prices and then they wonder why they find very strange betas. No, returns. right? Always calculate prices to returns first, and then you use returns to calculate variance, betas, and everything.
So here's my data. I've copied the information from the two downloaded spreadsheets into my working spreadsheet. These are the Amazon closing prices. Now we need to calculate the returns. The return is just the current stock price divided by the previous period stock price minus 1, expressed as a percentage. We do the same thing for this. And I can copy this all the way to the bottom, and this one too. We just need to delete the last observation because it does not have a previous stock price to compute returns from. Okay, so having done this, it's now straightforward to compute the beta. The beta is nothing but the covariance of the returns from Amazon to the returns from S&P divided by the variance of the returns from S&P, and that's what.
So this is what I mentioned. This is what we have not yet learned. Okay. So this way of calculating the beta, this actually comes from the capital asset pricing model, and we will talk about that after reading week. Okay. He will do the approach of calculating the beta that we did today as the next step, and you will see it's exactly the same thing. So there are two ways to calculate beta. First, you just use this covariance variance formula, or you fit the regression line and back out the slope of the regression line. It's the same thing. Okay? But this formula, there is no like super intuitive way to derive that without the background of the capital asset pricing model.
1.1067. Now another way to compute the beta is to use a slope function. The slope function gives the slope of the line that would be formed if you were to plot Amazon returns with S&P returns. So here Amazon returns are the known y's and S&P returns are the known x's, and if you do a slope you'll get the same number. I just need to increase the number of digits here to show that they're really the identical number. So these are two ways in which you can compute the beta for a stock compared to the beta for a stock market index. The things to remember are you want to use the adjusted close, and you want to make sure you choose the same time interval for both of the stocks. If you're using weekly for your S&P 500 or your stock market index, then use weekly for your stock index as well. So hopefully that should help with this. I hope you enjoyed this video. Thanks for watching. Hello and
Okay. Good. Any questions about that? So that's the index model. Okay. Simplification, not theoretically well founded, but it actually makes our life much easier. Okay? Good. So given that we already are relatively progressed in approaching the end of today, I will not start Unit 4. So we will talk about Unit 4 after the reading week. Give me 1 second. let me use a couple minutes to talk about things that we already know, just as kind of to refresh and make sure that everyone really understood those things, because I will go through some of the illustrations that I used during the lecture. And these are really kind of the core of the Markowitz world, and this will be very important to understand what follows, because this is, in some sense, this is really the foundation and the basis of the more advanced models. Okay? So, you all know that, but let's do it quickly, then we can stop a bit earlier today. This is our now very well-known, famous space risk-return, and we're interested in indifference curves. So we know in the risk-return space, there are multiple different risk-return combinations, right? So now we have two investors, Mary and Max. They both share the same utility function, and this is the same utility function that we will always use. But Max and Mary have two different levels of risk aversion. So Max is more risk averse than Mary. Okay? So how can we now draw their indifference curves? The first point, the first data point is simple. Where do both indifference curves start if this is an indifference curve for a utility of 0.1? They both start at 10%, right? Because the utility of the risk-free asset is exactly the return of the risk-free asset, always. Utility equals return if risk is 0. So both of their indifference curves must start here. And if you really want to draw it, I mean, there is no other way. You basically, what you do, you calculate different points and then you just draw it. So this is, for example, the indifference curve of Mary. All those risk-return combinations give her the same utility. If we draw the indifference curve for Max, will it be steeper or less steep? Steeper, right? Max starts at the same point, but his indifference curve is steeper. Max requires, if we add risk, for Max, the expected return has to go up more so that he ends up at the same utility. That's indifference curves. Okay? Same space. One risky asset, one risk-free asset world. So we had one risk-free asset, and we had a risky asset, F and P. Remember, we said, well, if we have F and P, I mean, of course, we can invest all our money in F or all our money in P. But these are not the only two options. We can form portfolios that consist of F and P, right? So then we call this the possible expected risk-return combinations. How is this called? The possible risk-return combinations are on the so-called CAL, the capital allocation line, right? So the line that connects F and P, this is the capital allocation line, and this shows us the possible risk-return combinations in this universe where we have only F and P. We also call that sometimes the investment opportunity set. So these are possible investments. So what does point A represent? Well, some portfolio that consists of approximately half F and half P. Right? What do points to the right of P represent? Talked about that. That is borrowing, right? I mean, here we assume same lending and borrowing rate, but that's not necessarily the case. If the lending and borrowing rate changes, what happens to the capital allocation line? It kinks, right? I mean, basically the slope here goes down. Okay? Generally speaking, what is the slope of the capital allocation line? Well, the slope of the capital allocation line is the risk premium, ER minus RF for P, so the expected return of the risky asset minus the risk-free rate, relative to the risk of the risky asset. So this is called the reward to risk ratio, or the reward to volatility ratio, or also the Sharpe ratio. It shows you how much expected return you get for taking risk. Okay? So, what is the Sharpe ratio for portfolio A versus portfolio P? Which Sharpe ratio is higher? It's obviously the same, right? I mean, every point on the capital allocation line has the same Sharpe ratio. So if you think about the optimal portfolio for an investor, I mean, you cannot simply say, oh yeah, I try to find the portfolio with the highest Sharpe ratio. I mean, that's nonsense, because all the portfolios on the capital allocation line do have the same Sharpe ratio, right? I mean, it's a straight line. A straight line has the same slope everywhere, okay? If you have borrowing, that's not, if you have different lending and borrowing rate, that's not exactly the case. So if you have a higher difference in lending and borrowing rate, actually the Sharpe ratio declines after P. It becomes lower, which is quite realistic, because your Sharpe ratio, if you have to borrow, I mean, typically is lower. Okay? Good. So what is the optimal portfolio C for an investor? Remember, we talked about different ways to find that. There was the graphical way, there was the brute force way, and there was the analytic way. So the graphic way, well, very simple. We try to fit in these indifference curves. And we remember that higher indifference curves go along with a higher utility. So this is a utility of 0.05 and this is 0.15. So the investor would like this higher indifference curve. But this one, unfortunately, is not possible because it never touches the investment opportunity set. There is just no investment opportunity that is on this indifference curve. So the optimal complete portfolio is at the end nothing else than the tangency point of this indifference curve. So this is the optimal complete portfolio. Right? If we have a different investor with a higher level of risk aversion, I mean, his indifference curve would be steeper and he would have a different optimal complete portfolio. Okay? This is the graphical solution. Remember, there was the brute force solution where you basically just for different discrete portfolios on this line calculate the utility, but this is not very precise. This just gives you a vague range where the optimal risky portfolio is. And if you do it analytically, remember, it was relatively simple. We set up the equation for the expected return of the complete portfolio, which was nothing else than the risk-free rate plus this risk premium times y, so the fraction we invest in the risky portfolio. The variance was very simple because we assumed that the risky asset and the risk-free asset have zero correlation, so things became quite simple. So then we set all of these parameters in the utility formula. So this comes here as ER, and this comes here as sigma squared. So then we have the utility formula for this complete portfolio. Very simple. Then we have the first derivative of that with respect to y, because y is our moving parameter. This is how we optimize. So we have the first derivative with respect to y. We set that to 0. So for y, and this is our y star, the optimal y. Risk premium scaled by risk and A. Okay? Simple. Good. This one we skip. This one we also skip. So if you remember then, we moved to the too risky asset world. So we left our one risk-free, one risky asset world and moved to the too risky asset world, so where we only had D and E. And we developed together that actually the investment opportunity set in this world depends on the correlation between D and E. So if D and E have zero correlation, it's something like this. this shape. So these are possible risk-return combinations if you combine D and E. But we said, well, if the correlation is 1, it's just a straight line. The correlation is -1, it's this 90-degree reverse change V shape. Right? This is the investment opportunity set for the too risky portfolio world. So this minimum something that I haven't really done in the lecture, so where I was a bit lazy, is actually to tell you what the optimal complete portfolio would be in the too risky asset world. Right? We never talked about that. We talked about the optimal risky portfolio, optimal complete portfolio in the one risk-free, one risky asset world, and we talked about it in the multiple risky, one risk-free asset world, but we never talked about it in the too risky asset world. And the reason is simply that it's not so easy, because this is basically, let me go back, this is basically your investment opportunity set in the too risky asset world. So this is the efficient arm because this one is dominated. So we have to find now the complete portfolio on the screen arm here that maximizes the utility for our investor. Unfortunately, there is no good analytic solution because this is not a straight line. This is like this curve, so things are more complicated. But we could still identify the optimal complete portfolio. I mean, we can do the graphic solution. We can just find draw the indifference curve and find the highest possible indifference curve. This gives us the complete portfolio. Or we can do the brute force approach and just calculate the utility for different points. But I will not show you the analytic solution because that's pretty messy. Okay? And the reason why we could skip that without actually, we have more risk averse, you're more here. The reason why we could skip that without losing a lot of generality actually is that this was still not a very this was still not a very realistic world, right? Because we had no risk-free asset. And luckily we saw when we reintroduced the risk-free asset, it becomes much easier to identify the optimal complete portfolio. Basically, we go back to our straight line and we have our analytic solution again. Why? Well, if we have D and E, this is the investment opportunity set. So we can, for example, invest in portfolio A, which is probably 80% D and 20% E. But as we know, we can not only invest in A, we can also combine A and F. So we can draw a capital allocation line between A and F. But we could also have a portfolio B, which is like, I don't know, 70% D and 30% E. So then we can combine B and F, and we have another capital allocation line. You remember we said then, yeah, look, we have an unlimited number of capital allocation lines, basically. But the good thing is we don't have to worry about that because there is only one capital allocation line that our investor will be interested in. And this is simply the capital allocation line with the highest possible slope, right? Because this one gives her the highest reward for taking risk. And this is the tangency line, and this is our optimal risky portfolio. Okay? I mean, of course, our investor would even prefer a higher slope, but unfortunately, capital allocation line question mark here, we cannot invest in that. It's not in the investment opportunity set. The investment opportunity set is only this yellow shape here. Right? We cannot do this one. Okay? The nice thing is now we have the optimal risky portfolio P, capital allocation line P. And now if we identify the optimal complete portfolio, we are completely back to our original problem of one risk-free, one risky asset, because we can safely ignore all the other risky assets. Right? Our investor only cares about F and P and wants to allocate his money between F and P. So we're nearly done. We then extended this world to many risky assets. So we said now we have a multiple individual risky assets and we can form multiple millions of portfolios based on these individual risky assets. So, but still, I mean, the investor is probably not really interested in most of these portfolios. right? So the first thing we did is we identified the so-called minimum variance frontier, which is for every given level of expected return, we identify the risk-return combination, the portfolio, that gives us the least risk, the lowest risk. So for this level of risk, expected return, this is the lowest risk I can get. For this level, expected return, this is the lowest risk I can get. Okay, and I can really all ignore all these other things here, because for a given level of risk, all these other portfolios have a higher risk. I don't like that. Right? And then we said, but wait a second, even on the minimum variance frontier, there are many assets that are not really great, everything on this lower arm, because everything on the upper arm dominates the lower arm. Right? For every level of risk, the lower arm had a lower expected return than the upper arm. So then we said, the upper arm of this minimum variance frontier, we call that the efficient frontier. This is where the investor is really interested in. Okay? And now, if you look at it, I mean, it's the same thing as the too risky asset world, right? I mean, once we have identified the efficient frontier, we are back in the too risky asset world, because the only thing we have to do is we find the tangency point. So the complexity in practice is really finding this efficient frontier. Right? Once you have that, things are pretty simple. And again, this is why we talked about the index model, because the index model makes it easier for us to find the efficient frontier. So now we have the optimal risky portfolio P, and then, yeah, optimal complete portfolio somewhere here, depending on your level of risk aversion. So this is basically portfolio theory, how we did it. And this will be the starting point for the theory, the equilibrium theory models. Okay? So this is also now the end of the content for the midterm. So unit 3 is now done. Unit 4 will be after reading week, but unit 4 will not be relevant for the midterm. Okay? Any questions about this? Good. So then we can stop 8 minutes earlier today. Thank you very much, and yeah, have a nice reading week.